In this and the next 3 slides, we are going to analyze an example taken from Shooman's book. As you see on the screen, there are 10 identical components that were put in service, and they all failed one after the other, and those 10 failure times were noted. And so they are starting from 8 hours all the way up to 266 hours. There are 10 of them. So we'll use this very simple data set to find the CDF of the time to failure of that component, the PDF, the reliability function, and the hazard function. So let's take this up one by one. And so let's first list the data in a table. So we have T starting from 0 all the way up to the last failure time, 266 hours, and the number of surviving elements drop from 10 all the way up to 0. So the number of surviving elements is 10 at t equals 0, obviously, and there is no surviving element at time 266. So first we are going to estimate the CDF of T capital F. So this is how we are going to use the estimation. So it is the number of failed units, N0 minus NT over N0. So let's take it up one by one. So what I have done, I've also taken the graph from Shooman's book for this problem. So but you see the CDF curve there, but we are going to derive this point by point so that we understand the process. So at t equals 0, there is no failed element, so CDF is 10 minus 10 over 10. So the value is 0, and that's the red point that you see. The next is at 8 hours of time. So we have one failure. So at 8 hours we have the next discrete point on the CDF curve identified, and that's the next red dot that you see. At the next failure time, 20 hours, we have the next dot. So that's 10 minus 8 over 10. There's a mistyping there. It's 10 minus 8. Anyway, so let's continue. At 34 hours, we have 10 minus 7 over 10, and that's the next red dot that we have plotted, and so on. So if we keep doing this, we are going to trace the curve that is already there from Shooman's book, or more correctly, we are going to get those red points and then join them with the best fit curve. But this would be the process of point-wise finding the estimated CDF. The x-axis, we have the observed failure times, and this is, there is one failure at each time that we have observed there. There could be other databases in which we could give number of failures in a certain interval of time. So we're going to see an example of that later on as well. So here we have the 11 points giving me the 11 estimates of the CDF of the time to failure, going all the way from 0 to 1. We continue with the same data set, and this time we estimate the PDF, the density function of the time to failure. So we have the same table, T going from 0 to 266 hours, and the number of surviving elements going down from 10 to 0. And we are going to estimate the PDF with our formula that we had put up a few slides ago. So it's the increment in the number of failures, or the drop in the number of survivals, over the original number of components and the time interval over which that happened. So basically we are differentiating the CTF. So let's do it point by point. Now obviously, since we have TI and the next step TI plus 1, we are not going to have 11 estimates as we did for the CDF, because now we are dealing with the derivative and we are going to only have 10 estimates of the PDF. So the first red point is for the interval 0 to 10, and we use the formula 10 minus 9 divided by 10, and the duration over which that happened, 8 hours. So that gives me 0.0125 per hour. And then the next one, it's the duration is now 12 hours, and that interval is identified by the second red dot that you see. This way, we move on to the next one, which is a duration of 14 hours, and that gives me 0.0071 per hour, and that is the third red dot, and so on until we can exhaust all our 10 intervals. And we can see a trend here. Definitely it's a drop. It could be an exponential drop. We don't know. We need further tests to determine that. But one good verification of whether it's an exponential time to failure or not could be guessed if the hazard function is kind of a straight line. If we see a more or less flat hazard curve for the entire range of observed times, then we would be more convinced that this is probably coming from an exponentially distributed time to failure. So we proceed. The last interval has a duration of 80 hours and one failure, obviously. So that ends the PDF with 0.00125 per hour. The next function to look at for the same data set is the reliability function. So here is the table once more. We have the times observed at each successive failures, T going from 0 to 266 hours, and number of surviving elements dropping from 10 to 1, 10 to 0, and we would like to use the expression that you see on the screen to estimate reliability. So it's number of surviving elements at time t over the original number of elements, n0. This is the graph reproduced from Shooman's book, and let's make sure that we can reproduce it from the data. So the first one is at time 0, reliability is 1, so it's 10 surviving over 10 original, and then the next one is 9 over 10, and so on. So there is no surprise there. We have done the complement already with the CDF, and so we climb down from 1 all the way to 0, going through each observation of failure. And then once we are done with these 11 points, we could join them with piecewise continuous lines or a smooth curve and estimate the reliability function. The area under this curve would be, as we have derived before, the mean time to failure. The last function we estimate from this data set is the hazard function. So let's put the table on the screen first. So we have the observed times to failure, the number of surviving elements, and then we are going to use the formula nt minus nt plus nti minus nti plus 1. So again, we are estimating with one step forward, so we'll be able to have only 10 estimates, and then that divided by the number of surviving elements at the time instant of interest, and divide that by the length of the interval. So if you remember, we are dividing the density function with the reliability function. So let's do that step by step. This is the result taken from Shooman's book. But let's make sure that we get the same answers. So the first one is one failure, so nti minus nti plus 1, so delta n is 1, which is the same for all these observations, all these intervals that we have, but the number of the length of the time interval is not the same, so that's going to create some difference. So we have 10 minus 9 divided by 10, so which is the current number of surviving elements, and that divided by the length of the interval gives me 0.0125 per hour. That is the hazard corresponding to the first interval from 0 to 8 hours. For the next interval, 8 to 20 hours, we have one failure with the initial number of failures, initial surviving numbers being 9, and the length of the interval 8 to 20 is 12 hours. So that gives me 0.0093 per hour. The third one again has an interval of 14 hours and 8 items to start with. So that gives me 0.0089 and so on. So we continue down the list and we can trace all the numbers, and more or less I think the answers match perfectly. And so we come to the interval number 8 and then number 9 and then 10. So what we see here, as we had suspected when we are looking at the PDF, is that it kind of looks like an exponential drop, and here we have a hazard function that one could argue very convincingly that it's more or less a flat constant line, a horizontal line. So there is reason to believe, there are good reasons to believe that this time to failure is exponentially distributed, and within noise, within observational error, we have observed a more or less flat hazard curve. So this would be the way that we would analyze a simple data set of observed failure times when we do not have any parametric tests in mind. We are not fitting to any particular distribution. We do not have any underlying assumptions. All we have is the data, and we are estimating the hazard function, the reliability function, and the mean time to failure if necessary from the data itself without bringing in any additional assumptions.